In this screencast, we're going to explore the low boiling points of alkanes when compared to molecules of similar molar mass. We're going to look at a few patterns, and then I'm going to give you 3 tips that can help you solve any alkane ranking boiling point problem. So to start out, I've listed the names of a few alkanes: methane, butane, pentane, 2-methylbutane, and cyclopentane here on the left. I've listed their condensed structural formulas. In red, their boiling points, and then also their line angle or skeletal formulas over here. Okay, so if we just look at this information to start, we can notice that methane, our smallest alkane, has a boiling point of -164, whereas a longer alkane, pentane, with its 5 carbons, has a boiling point of 36 degrees Celsius. So right off the bat, it seems to be that the longer the chain, higher the boiling point. And we noticed a couple other things. I have some isomers here. The branched one seems to have a lower boiling point than the straight chained. And of course, the cyclic one seems to have the higher boiling point of all. So let's try to figure out what's going on here. The first thing we should probably do is figure out what does it mean to boil. And a good thing to do also is to compare the boiling point of something that is very familiar to us, water, with something that isn't quite as familiar with us, but our hydrocarbon methane. Okay, so a couple of things. Water's molar mass is going to be 16, 17, 18 grams per mole. And in comparison, methane, 12, 30, 40, 15, 16, its molar mass is 16 grams per mole. So they're pretty close as far as molecular weight goes. We know that at STP, water boils at 100 degrees Celsius, and on our chart before, we saw that methane boils at -164 degrees Celsius, okay, which is almost 1.5 times lower. Okay, so why does this happen? Well, water is a polar molecule. And this is really going to be what makes the difference. Methane is nonpolar. Okay, so we need to figure out, what does it mean to be polar? What does it mean to be nonpolar? A polar molecule like water means that if we look at the molecule itself, it has a negative and a positive side, or slightly negative, slightly positive. So around the oxygen end right here, our water molecule has a negative charge and slightly negative, and near the hydrogens it has a positive charge, and this is what makes it polar, negative and positive. Instead of north and south pole, we've got a positive and negative pole. What that means is that if we put another water molecule right near it, okay, they're going to make a strong type of intermolecular bond. Negative here, positive here. Anytime we have opposite charges, they attract. So between the oxygen atom of one molecule and the hydrogen atom of another molecule, we have this intermolecular between molecules bond called a hydrogen bond. Okay. In comparison, if we look at methane, CH4, that's just my dog. Okay, so methane, falling asleep at this, methane CH4 doesn't have a negative, really negative or positive concentration. Carbon and hydrogen share electronegativities. So what that means is no one's an electron hog. The charge is pretty evenly distributed. So for example, if we have another methane here, no hydrogen bond forms. We need an electronegative for that, an electronegative atom for that. Okay, so how do 2 methane molecules stick together? They stick together by weak intermolecular bonds called dispersion forces, or London dispersion forces. Okay, and those dispersion forces are temporary, instantaneous, short-lived forces that are caused due to the electrons moving around within the atom, within the molecule. For example, antiatoms. For example, carbon here, if its electrons were slightly, let's just say on this side of the carbon atom, then over here, the hydrogen, that would have a little negative charge. Over here, hydrogen would be slightly positive. Let's say the same thing happened to this carbon atom. Then for a very short time, we would have a London dispersion force, a stickiness holding these two together so that, that this could be a liquid. Water also has London dispersion forces, but the hydrogen bonds are so much stronger than the dispersion forces. Okay, so the alkanes have low boiling points because they're nonpolar. That would be the main answer there. All right, let's kind of go back, if we can, and look at the comparison of boiling points among the alkanes. So as we noticed before, the longer the chain, the higher the boiling point. And because boiling really is taking these molecules and separating them. So we add enough heat that at 36 degrees Celsius, STP, the blue pentane and the green pentane are going to separate from each other, and what we're going to have is pentane in its gaseous state. Okay. The longer the molecule, the more London dispersion forces, the more stickiness. So the bigger the molecule, higher the boiling point. When we have this branching pattern right here with 2-methylbutane, the boiling point's a little bit lower. If we notice these two are isomers of each other, so they both have 5 carbons, and if we count up the hydrogens, we have 3, 6, 7, 8, 9, 10, 3, 6, 7, 8, 9, 12. And down here, we also have the same thing, C5, H, if we add up all our hydrogens, 12. So they're isomers of each other, structural isomers, same molecular formula, different structure, different boiling point too. So where this is 36, this is a little bit lower at 28 degrees Celsius. And that's because right here, this methyl group is going to prevent this close packing if we have 2 of these together. Another one up here. They can't get as close together, so we have not as many points of contact, a little fewer dispersion forces, therefore a little less heat is needed to shake these 2 apart into a gaseous form. Okay. Now when we look at cyclopentane, that C has the highest boiling point of all of these. That's because when we look at this carbon-carbon bonds within here, it's a very rigid, more rigid structure. And so these cyclopentanes can stack upon each other very closely. There's more points of contact, there's more attractions, and that's why we have the higher boiling point. Okay, so let's summarize these trends. So alkanes with the greater molar mass have higher boiling points. Straight-chained alkanes usually have higher boiling points than their isomers. Cycloalkanes have higher boiling points than their straight-chained counterparts. Just to see if we are on the same page here, let's do a couple of practice problems. And so what we're going to do is rank these, and we're going to circle the one that has the highest BP, the highest boiling point. Okay, so between pentane and heptane. Pentane, that's 5 carbon straight chain. Heptane, hept is for 7 carbon straight chain. The longer the chain, the higher the boiling point. So you've got it. Heptane would have the higher boiling point of this pair. This pair, propane or cyclopropane, we notice cyclo here. So we would have each molecule would be 3 carbons joined together in a cyclo, whereas propane, 1, 2, 3, would be a straight chain, straight chains right here, versus the stacking and more points of contact if we were to kind of try to pile these up. Okay, so the one that's going to have the higher boiling point is going to be the cyclopropane here, more stickiness, tighter packing. And then between hexane and 2-methylpentane, we look at these, the branching, they're not going to be able to pack as tight together, so therefore our straight chain hexane will have the higher boiling point. Okay, thanks very much, and I hope that helped.